Hey everyone, this is going to be a big video on the topic of magnetism. Magnetism and electromagnetism, which is magnetism and electricity, is a huge topic and there's so much in there. I've decided to put it all into one huge video, but I don't expect you to watch the whole thing necessarily in one sitting, so I've put timestamps in the description for every kind of major topic, so skip along if you need, go back and forth, however helps you. So magnetism is all about, of course, magnets and magnetic fields. And we all know what a magnet is. We deal with them probably reasonably often. You might have fridge magnets or magnets in various things around your house. So what exactly is a magnet? How does it work? Well, magnets, I'm going to draw them like this. Here's a magnet. And it has a north pole and a south pole. This is kind of just a normal bar magnet. There's many other types. Every magnet has a magnetic field around it. And magnetic fields go around the magnet like this. They go from north to south, from north to south. And there's lots of different lines. That's what a magnetic field looks like. These field lines are called B fields. And we're going to use that term a little bit as well, but B field and magnetic field are interchangeable. B fields always flow from north to south, you can see. They form loops kind of around the magnet. They never cross, so there's no B field that's like, oh, crossing like this. No, never. B field intensity, basically how strong these are, can be measured, and it's measured in a unit called the Tesla, named after Nikola Tesla, which we use the letter T for. So this is what a magnet with a magnetic field looks like. One other piece of information kind of here is this thing called the law of magnetic poles. And the law of magnetic poles basically just says that opposites attract and similar poles repel. And this is something you've probably learned for years. North plus north, they repel. But north plus south, it attracts. Opposites attract. That's the law of magnetic poles. Okay, now we're going to move on to a topic called domain theory. So domain theory. Anytime you have a large magnet, like really anything bigger than like atom size, so all the magnets you see in the real world, these large magnets are actually an illusion. They're made up of smaller magnets inside, and these smaller magnets are like atomic. And they're called dipoles. And dipoles do this thing where they align in the material. So notice how all these dipoles are aligned. They're going along straight lines here. And each of the dipoles, which is in itself a tiny magnet, are aligning north of all the dipoles here and south of all the dipoles there. When the dipoles in a material are aligned, we get magnetization. The material becomes magnetized, and a magnetic domain, which is all these fields around it, get produced. Now, if you this might have happened to you in real life. If you ever drop a magnet or crash it really hard or heat it, you can actually demagnetize it. And what's actually happening is these dipoles are getting misaligned. This one might like be spinning off this way. And when they're misaligned, they don't form a bigger magnetic attraction or a magnetic field. And so you don't get an overall magnetized thing. One important definition here is the word ferromagnetic, which is a very long word, but there's magnetic in it, and ferro, which just means iron, because it was one of the first magnetic metals to be discovered, was iron. Ferromagnetic materials are materials that are naturally magnetic. So, pieces of iron are magnetic just by default. Nothing is actually magnetic by default. What is actually happening is the iron is magnetized by the Earth, because the Earth has a giant magnet at its core, we all know. Okay. Next topic. This is something called magnetic permeability. And so let's think a little bit about what this means. Magnetic, obviously, it has to do with magnets, and permeability, which is typically a word for like how easily something can move through something else, how permeable something is, which is kind of right. all materials in this world, like everything in the world, has a property called magnetic permeability, which is a measure of how magnetizable something is. How easily can a material be magnetized by a field? And so magnetic permeability uses the letter mu, which we've seen before referring to friction, but now it refers to magnetic permeability. And there's a couple additional letters. So this is normal magnetic permeability, and it's mu. Now, if you ever see mu with a 0 subscript, this is a specific material's permeability. This is the permeability of what's called free space. And free space just means a vacuum. So it's not air, it's free space or a vacuum. The permeability of that is mu 0, and it's a specific number. It's equal to 4 pi times 10 to the negative 7, but that's not really important to know. Mu 0. Then there's another concept. In addition to normal magnetic permeability, we also have something called relative permeability, which is mu with an R. Relative permeability is how more or less permeable something is compared to the free space. So a material with a relative permeability of 2, that means it's twice as permeable as a vacuum, which means that it can be magnetized twice as easily than compared to like empty space. Now, you can divide up materials into categories based on how permeable they are. And there's 3 categories. The first ones are called diamagnetic materials. The second one are paramagnetic materials. And the last one are ferromagnetic, which we heard about before. So, diamagnetic materials are materials where, and I'm going to write this, mu r is less than 1. That means that the relative permeability of a diamagnetic material is less than free space. That means it's actually harder to magnetize than nothing. This means that when you add this material to something or use it in something, you're actually decreasing the overall magnetism. An example of this is gold, for instance. Gold has a permeability of 0.99996, which is not quite 1, and therefore it's diamagnetic. Paramagnetic materials have a permeability of just over 1. So it's greater than 1, but barely. These are magnetic, but not really magnetic, and you would need a strong magnetic field to get them to magnetize. They're not easily magnetizable. An example of this is something like aluminum, which we don't even think of as really being magnetic, but if you have a strong enough magnetic field, you can get it to be magnetized. Aluminum, for instance, has a mu r of 1.00002, which is just barely over 1. And finally, we have the ferromagnetic materials. These are mu r of over 1, but above the paramagnetic, so quite a bit. These are what we would consider magnetic in the normal world because they're magnetized even by the Earth. So an example of this would be iron, which has a massive 5,000 as its mu r, as its relative permeability. So it's 5,000 times more magnetizable than free space. Okay, we've talked a little bit about these general topics. We're now going to get into specific types of magnets, and I'm going to kind of explain each of them. The first type of magnet we're going to explore is called the straight conductor, which is precisely what it says. A straight conductor is a conductor that's straight, pretty much. Now, here's an example of a straight conductor right there. Now, straight conductors obey a law called Oersted's principle. Oersted's principle. And what Oersted's principle says is that anytime current moves through a conductor, so if you put current through this conductor, like with a battery here, it produces a magnetic field around the conductor. This is actually true of anything. It doesn't have to be specially designed. If you have current flowing through something, it will be magnetized, even slightly. Now, these magnetic fields, first of all, they exist only while current is flowing. So only while there's current will you get a magnetic field. If you turn off the circuit, if you remove the current, the field is gone. The field is orthogonal to the current flow. Now, when I say orthogonal to current, what I mean is that it's at a right angle to the current. So the current is going through this way. The field is doing stuff like this at a right angle. And finally, the strength of the field depends on the amount of current. More current means a higher strength field. There's actually an equation to describe this, and the equation looks like this. Now I'm going to explain each part of this. So we already have met a couple things here. I is the symbol for current. We know this from our video on electricity. And B brings to mind B field, which is what it is. It is the strength of the magnetic field, the value we're trying to find. We already know mu0, it's the permeability of free space. And then finally, we're dealing with 2 pi r, and r is literally just the radius that we're measuring this away from the conductor. So, here's a conductor like going into the page. If I measure it here and this is 2 centimeters away, there's your radius. If I measure the field here, well, that could be 4 centimeters away, and that's your radius. So this equation right here is how we describe the field strength of a straight conductor, and you can use this. Now, straight conductors also follow something called the right-hand rule, and all conductors follow a right-hand rule, but unfortunately and kind of confusingly, there's a bunch of different right-hand rules. So I'm going to call this one the right-hand rule for straight conductors. Now, we have this notation system that we use in physics, where if I draw a circle with a dot, this is a conductor that is facing toward me, so it's coming out of the page, or for you, out of the screen. And if I draw here with an X instead, that's going into the page, or into the screen. So that's important to remember. So the right-hand rule gives you a relationship between the direction of the current flow and the direction of the magnetic field, because these magnetic field lines are concentric circles. So they form circles that go around like this. And the direction of these, whether it's going, top to bottom in this or bottom to top, is given by this right-hand rule. And so what does the right-hand rule say? Well, unfortunately, I can't show you because I'm writing on the screen here, but you just do what I'm telling you to do with yourself right now in front of the screen. So, if you take your right hand, it's called the right-hand rule, you're always going to need the right hand. Take it, and in this first diagram, the current, remember, is pointing out of the paper toward me. So take your hand and point the thumb toward you, so it's in the direction of the current. When you do that, then make a fist. When you make that fist, your fingers will curl in a specific direction. In this case, the direction that my fingers curl is this way. And that is the direction of the magnetic field. So remember, if current is coming out of the page, magnetic field is going counterclockwise. The right-hand rule says, that you always point your thumb, goes in the direction of current, and that then your fingers will curl in the direction of the magnetic field. Here's the opposite example. Put your thumb toward the screen or away from you and curl your fingers again to make a fist, and you'll notice that this time it's going the opposite direction. And so that's how the right-hand rule for straight conductors works. Okay, the next type of magnet we're dealing with is something called a current loop. And a current loop is basically a straight conductor that got bent. Here's a straight conductor, here's a current loop. It's just a loop of a straight conductor. Because of that, it follows almost the same rules. It has the same right-hand rule, and it does make the same concentric circles around it for fields. The only difference is its formula is slightly different. The formula for a current loop looks like this. And if you notice, the only difference between this formula is the formula for the straight conductor had a pi beside the 2r, whereas this doesn't. That radius is literally the radius of the current loop. Again, they follow the same right-hand rule, same everything. They're kind of just a side note here. Okay, now we get to the exciting part, solenoids. Here is a solenoid. I'm going to just draw a kind of, admittedly not beautiful drawing of one, but it'll do. This is a solenoid. A solenoid is a wire that's been wrapped around some core material. That core could be, something like iron or aluminum, or it also could be air or theoretically vacuum. The core doesn't always have to be there. But there is a core material here, and there's a coil of wire wrapped around it. Solenoids usually have a stronger B field intensity than straight conductors because there's so much more conductive material in a small space because it's wrapped around. Look how many loops are in this space. Solenoids have a different formula for field strength, which looks like this. Now, we already know what B is, but all the other letters are new to us. Mu is the permeability, but it's not the permeability of free space anymore. Now it's the permeability of the core material, whatever it's made out of. Then we have N. N is the number of turns of this wire. So, for example, my solenoid over here, that isn't actually a very good one, has 5 turns. 1, 2, 3, 4, 5. And so it would have an N of 5. I is the current being passed through the solenoid, which is the same as in the last equation, and L is the length of the wire. So this formula tells us some important things. First of all, when we deal with the values of mu, of N, and of I, as they get larger, the field strength increases. So mu getting larger equals larger field strength. N getting larger is a larger field strength, and I getting larger is a larger field strength. L, on the other hand, L getting smaller is a larger field strength, and that's because it's on the bottom of the fraction, whereas the other things are on the top or beside it. So, all these things, as it gets bigger, so does the field strength. L is the opposite. As it gets smaller, the field strength increases. So from this, we can see that an optimal solenoid, like the best one possible, has the most permeable core, so the most easily magnetized core possible, the most current going through it possible, the highest number of turns possible, but with the shortest wire. So you notice how number of turns and wire length have this relationship, because obviously adding more turns does increase the length. So there's a trade-off here. You're going to hit a point where if you're trying to make an optimal solenoid, adding more turns will actually be less helpful because the length becoming longer is disadvantaging you. Now, solenoids have this advantage that you can turn them on or off easily with a battery. So you can put a battery here, and so because they're so strong and they can be turned on and off with electricity, they're used as electromagnets, magnets that can be controlled with electricity. All sorts of things use these. Speakers, sound systems, car starters, even like locks, all make use of solenoids. Finally, solenoids have a right-hand rule, but it's different than the right-hand rule for straight conductors. This time, it's almost the exact opposite. If we have a solenoid here, that's going like this, here, this solenoid, this is what you do. You take your fingers and you curl them in the direction of the current flow. So let's say I put the battery like this. Current is flowing this way, right? So current is going into it and it's coming out and going in and this way. So I curl my fingers in that direction. And when I curl my fingers in that direction, going kind of up and over, which means that the back of my hand is facing me, you can see where the thumb points. And the thumb is pointing this way. That becomes north. This is the right-hand rule for solenoids. When it's coming over, it's going over, and you have the direction, the thumb is pointing north. This is the exact opposite of the right-hand rule for straight conductors, because there we use the fingers for the direction of the magnetic field and the thumb for the current. This is the opposite. Okay. Next topic is motors. Now, motors, we see them everywhere in daily life, literally all over the place, in cars, obviously, and in so many other things. How do motors work? Motors are based on a principle, which is called literally the motor principle. What a great name. The motor principle tells you a couple things. First of all, when you have two magnetic fields and they interact together, you'll actually get a force. It creates force. This is kind of cool and is kind of the foundation of the motor principle. Now, if the conductor that carries a current, so if you have a conductor carrying a current and you put it into an existing magnetic field, you'll get a force that's perpendicular to the conductor's charge flow and the external magnetic field. So this is probably not super helpful without visualization. If the external field is going like this, and you have a conductor coming in like this, then the force will be in this direction or maybe that direction because that is perpendicular to both of them. Finally, the strength of this force depends on the strength of the external magnetic field and the current through the conductor. So the field and the conductor current both matter here. And finally, so to summarize this, basically if you have a straight magnetic field that goes in a certain direction, so that's the orange lines here, they're going, let's say, this way. This is a magnetic field. If you then put a curved magnetic field, so that's one of these, a straight conductor or something like it, which has these circles around it, and you put it on top of it, you'll produce a force. And so this is basically how motors operate. Motors have a right-hand rule too. I'm calling it the right-hand rule for motors. The right-hand rule for motors basically works like this. This time, you have your palm outstretched. It's not in a fist. Still the right hand. Your thumb points in the direction of the current flow. So here, the current flow, let's say there's a dot here in the center, which means that the current flow, remember, is away from the page. So my thumb points out of the screen, out of the page. Fingers point in the direction of the B fields. So these orange fields, which are going from a north to south here, the fingers point toward the south. They point in the direction. So that means your hand rotates a bit, your thumb is still towards you, and your fingers are going in the direction of the orange. Finally, what you have left here is your palm, and your palm will be facing the direction of the force. So for me, I put my right hand, thumb toward me. I put my palm ends up facing up because of that. And so because the palm is facing up, we can conclude that therefore the force is facing up. And that's basically it. If there was a force here, the force would be exerting in this direction. So DC motors use an electric current running through a conductor, literally like this blue one here, which generates a circular magnetic field. This interacts with an external magnetic field, that's the orange lines, which is usually set up because there are two magnets here and here, which create that field. And then because of this, you get a force that rotates the motor around. Now the design of a motor is kind of complicated, but if you check the description of this video, I've put a link to a really cool video which does 3D modeling and a 3D animation of a motor, and that'll explain it much better than I ever could. Alright, the next topic here, we are going to talk about induction. Now, induction is based on the work of this guy named Michael Faraday, who was a scientist and an engineer, I think, who worked on magnetism and electricity. He created Faraday's law. Faraday's law is also called literally the law of electromagnetic induction. Faraday's law is pretty simple. It says that a moving magnetic field near a conductor will induce current flow in the conductor. That word induce basically means that it'll make it appear. So, a moving magnetic field, and remember it has to be moving, when you put that magnetic field near a conductor, it'll induce a current flow in the conductor. It'll create a current flow, it'll make it appear. There are some factors which will affect the amount of induced current. The number of turns on the coil that is inducing the current, the rate of change of the field, because remember it has to be moving, and the strength of the field. Strength of the field, rate of change, and number of turns are the things that affect it. Now, Faraday's law is one important component of induction. Another important component is Lenz's law. Lenz's law is, I'm going to admit, a bit confusing to understand, but don't worry, it's not super important, and I'll try and explain it as best as I can. Lenz's law is basically the every action has an equal opposite reaction law that we learned in the unit on dynamics, but for electromagnetism. It says that the direction of an induced current will create a force that opposes the motion of the magnetic field. Basically, when you use a magnetic field in a certain direction to induce a current, because you'll have a field that's going to induce current, that current will then turn around and create a magnetic field in the exact opposite direction. Basically, you have a coil here. The coil is going to induce a current in this circuit, which has a straight conductor, show, as an example. So you don't actually need a battery. There's maybe a lamp here, because the coil will induce the current if it's being powered. And when it induces this, the current that's flowing through this conductor will also start creating a field in return, because straight conductors create fields. And you'll get a field in the exact opposite direction. And that's the important part. Every field has an equal but opposite field, you could say. So that's what Lenz's law is. Not super important, but it is an aspect of induction that is worth knowing. Okay. Now remember, electromagnetic induction is used in lots and lots of places. Generators, transformers, induction stoves, metal detectors, all examples of technology that use electromagnetic induction. But we're going to look at a couple in particular. The first one we're going to look at is a generator. Woohoo! Generators. Now, generators generate power. But that's not really a helpful definition. What generators actually do is they, first of all, create electricity. And second of all, they convert different types of energy from one form into electrical. So some generators may start with thermal energy and convert thermal into electrical. Others may start with gravitational energy and convert gravitational energy into electrical. But the ones we're going to look at today, and the most common, take kinetic energy, which is motion, and convert it to electrical. Now, it's based on the principle of electromagnetic induction, but what might blow your mind about a generator is that the design of a generator is the exact same as the design of a motor. When you watch that video with the 3D animation of a motor, that's also how a generator looks. The only difference is that they're working in the exact opposite direction. A motor takes electrical energy, you power the motor, and it creates a magnetic field that creates a force that moves the motor. So it converts electrical energy into kinetic energy. That's a motor. A generator does the exact opposite. It uses kinetic energy, so turning it or something, and it exposes that to a magnetic field to induce a current. So it converts kinetic energy to electrical energy. So it is a generator. So this kinetic energy can come from a bunch of sources. In Ontario, for instance, you might have heard we use hydropower, which is short for hydroelectric. And that means that the kinetic power that we're looking for is coming from moving water that's falling over these huge water turbine structures. All right, and our final topic, which is another application of induction, transformers. Transformers are used when we have a source of electricity, but we need to change either its voltage or its current. So we need to transform the electricity in some way, transformers. Transformers are super simple in terms of design. It's literally, imagine that's a solenoid coil. It's literally two solenoids put basically back to back with a little bit of space in between them. Now, we name these coils the primary coil and the secondary coil. And that's because you put the power into the primary coil, so it's primary, and you get it out of the secondary coil. Power in, power out. So, there are two types of transformer. There are step-up transformers, and there are step-down transformers. And the step-up or step-down is referring to what happens to voltage when you put it through the transformer. A step-up transformer steps up voltage. The voltage coming out is greater than the voltage going in. Whereas a step-down lowers the voltage. The voltage coming out is less than the voltage coming in. But transformers can't create or destroy energy. They can just convert power from voltage to current or current to voltage. So, if they increase the voltage, that's a compromise. In exchange, they're decreasing the current. And if they decrease the voltage, that's also a compromise because they're increasing the current. So a step down actually increases current, and a step up actually decreases current. Now, transformers work because the number of turns of the primary and the secondary coil are different. So this creates a difference between the input voltage and current and the output voltage and current when the first coil induces a current in the second coil, because they have a different amount of turns. Also, because transformers are all about induction, they need a changing magnetic field. Remember, you need a moving magnetic field for induction, Faraday's law. And so transformers only work with AC power, which is alternating current, stuff like you would get out of your plug. They do not work with DC current. Finally, transformers have a fun formula. The formula for transformers looks like this. And in this formula, you'll recognize V and I are the voltage and the current. And P and S are just primary and secondary. So VP is the voltage going in, the primary coil voltage. VS is the voltage coming out, the secondary coil voltage. So you notice that there's an inverse relationship here between the voltage and the current. As the voltage gets higher, the current will get lower, and vice versa, because you can see that the fractions are literally switched. You can also see that voltage works the same as turns. More turns is more voltage, because these are not switched. And this is helpful if you ever get a transformer and it just tells you the number of coils, or number of turns on each coil. You can use that knowledge to figure out whether it steps up or steps down, because if the number of coils on the secondary is larger, that's a step up, and if it's smaller, that's a step down. Alright, that is it for this video. We've covered a bunch of different concepts. We went through basics of magnetism, domain theory, magnetic permeability, straight conductors, current loops, solenoids, motors, generators, transformers, and induction. Hopefully this gave you a bunch of information. Feel free to skip around to those timestamps, and please check out that motor demonstration. It's very cool. And hopefully this was helpful to you. Thanks for watching.